Assalamualaikum and selamat sejahtera. This time, you will apply all the knowledge gained from the previous topics to understand the operation of single-phase, fully controlled rectifiers. To highlight the differences, I will begin all my explanation with uncontrolled rectifiers. First, we will start with the circuit topology. Based on the circuit of both half-wave and full-wave rectifiers, we can see that all the circuits are constructed using diodes. Now, let's convert the circuits to be controlled rectifiers. As you can see, the framework of each circuit is remaining unchanged except the power switches. Next, we will focus on the principal operation of the rectifiers. As discussed in the previous videos, I said it is easy to explain the principal operation by referring to the supply voltage waveform. As you know, during the positive half cycle, diode D in the half wave, diode D1 and D2 in the bridge, and diode D1 in the split supply rectifiers are forward biased. It is because the polarity of the anode terminals is positive. Automatically, the diodes are turned on and conduct the current. Now, we will consider the principal operation of controlled rectifiers. As you can see in the flowchart, the thyristors is not working in the forward bias even though the anode terminals is positive. Instead, the thyristors are ready to work in forward bias with the presence of a control signal. Once the control signal is applied to the gate terminals, the thyristors are turned on and conduct the current. Meanwhile, during the negative half cycle, thyristor S in the half-wave rectifier is turned off. However, in the full-wave rectifier, thyristor S3 and S4 in the bridge and S2 in the split supply rectifiers are turned on when the control signal is applied. By considering the whole operation of the control rectifiers, we can conclude that the time of injecting the control signal determined the starting time of the current conduction. Based on the graph, the time is referring to the angle value at the x-axis. Then, we can use these equations to sketch voltage and current waveforms. Now, we will consider a control rectifier with resistive load. Based on the circuit, we need to change the level of equation 3a, 3b, and the bottom waveform to Vt. Next, we will focus on the graph. Please remember that the thyristor can only turn on during the positive half cycle of the supply voltage. Thus, we just need to apply a control signal during that half cycle. Since the thyristor is a current control device, hence, the control signal is in the form of a current pulse. And it is injected at omega t equals to alpha. The alpha is known as firing angle and it indicates the starting time of the current conduction. Based on the angle value, we need to adjust the conduction range as follows. As a result, the conduction range of the thyristor is shorter than the diode in the uncontrolled rectifier, and subsequently, it reduces the conduction angle of the thyristor. Furthermore, due to the new conduction range, these equations are only valid when the omega t is in between alpha to pi. Because of that, we must consider the operation of the rectifier before the firing angle. Since the rectifier is turned off before alpha, hence we can remove the thyristor from the circuit. And we can have these equations by analyzing the circuit. Based on these voltage and current equations, we can see that we need to chop the output voltage and the output current waveform before alpha. Additionally, we need to sketch the waveform of the thyristor voltage as similar as the supply voltage waveform. According to the new output voltage and current waveforms, we can conclude that the function of control rectifiers is to chop the output voltage and output current waveforms at a specific angle. Hence, it reduces the output voltage supplied to the load. The output voltage can be controlled by regulating the firing angle. And if you want the rectifiers to operate at maximum condition, we must set the firing angle equal to 0.